what is the goal here? The goal is to minimize. I don't want just a yes no answer as a map estimate. Goal is to minimize magnitude of error. Okay. So here the choice is squared error. I'm doing a squared error. I have discussed about that also, why squared error is important and not absolute or just the difference. Okay. So if you have just the difference, right? So for example, if I have a share price that is 1000 and one day I'm making prediction of 980 and one day I made a prediction of 1020. This is minus 20, this is plus 20. And say both the days the cost price was 1000 only. So if I just do a simple sum, then net will be of both the days will be of all the predictions if I'm doing it. So net will be minus 20 plus 20 will cancel out and I'll say 0, that I have made exactly correct predictions, right? So that is not there, but I have made mistake in both the cases. That was off by 20 plus 20 minus 20, right? So this is wrong, that I cannot just do a simple summation. So that's why we do a square of it, so that the error term is amplified by square. So this minus 20 will, if I square it, this will become 400, will become 400. So this will give me the magnitude of the mistake I have made. And I want to know how much off I am, how much wrong I am. I want to get that magnitude only. And I want to minimize that magnitude so that I'm close to the value that I want. And that's what all mean squared errors do. It will give me the magnitude, how much I'm off, and the squaring will just amplify that impact. That's why we go for squared errors. Okay, there are other reasons also. I'll discuss about that in detail when I'm talking about machine learning algorithm, etc. And we have to minimize this. And here again, same thing. We are doing an estimation of the parameter, and we have to minimize the how much error we are making in the estimation. So if I have the parameter of the distribution of the data, so the net error should be minimized. That's the task. Let's see. So what does MMSE do? MMSE, okay, what does it do? So it minimizes the posterior mean. So posterior mean, okay. So if I find the mean, minimizes the mean squared error. If I find the mean of that, and if that is my estimate, if my estimate is okay, if my estimate is that if I find the mean itself of that whatever is that distribution, so and if that is 1 point estimate, so that will my minimum, that will give me my minimum error, because this is distance from the mean. If I predict the mean itself, this will minimize the complete thing. So if I have the posterior distribution and if I predict what is the mean, so all the errors that I am making, this whole net mean square error will be reduced. So I want to predict what will be the mean. Earlier, what did we do for map? We found the peak. Okay, we found the peak. What is the peak of that distribution? But here we want to find the mean of that distribution. Okay, even map, if it's a skewed distribution also, we want to find the peak. But here if I have the mean will be somewhere here. Most of the values this side. Okay, so that's what we want to find, so that our net error, that is the distance from the mean, is minimized. Okay, so what is the task? So how do we calculate mean? The mean is the expected value. Okay, what is the mean? Expected value in terms of okay. So mean is the expected value. So what is my task? The task is to find what is the task? Task is to find expected value of parameter theta, okay, given the data. So I have a data, so I have to find the expected value of the parameter theta given the data. Okay, that is the conditional expectation. This is given. So what is that? That is our posterior, right? So that is p theta given x. This is what we want to find. So I have to find the mean of this. This is we are getting a distribution here, and we want to find the mean of that distribution. Okay, so how we do expected value? How do we write expected value? So my theta MMSE will be equal to minimize. Now we are minimizing arg min theta, and then expected value of the mean squared error. So this predicted theta of x minus actual theta whole square. The expected value of this we want to minimize. Okay, and this will be coming from, this is my posterior. So expected value, so this is the posterior, this is the distribution, this is the distribution of my of the parameter after I have seen the data. So what is the formula for expected value? So if not, check the value or check the video. I'll put the link in the description for the expected value. Okay, explanation what we have done. So this will be equal to sorry, this will be equal to sigma over theta. Okay, and this will be, I'll just write it other way around. So generally this is the probability. Okay, probability of theta. So we see the probability into x, right? Theta given x, theta given the posterior into theta d theta, and if it is discrete, integral over theta f of theta given x, theta given x into theta d theta. This is for discrete, this is for continuous. That's what we do, right? The values of the theta into their probability, value of the theta into the probability, and the summation overall for discrete, and the complete integral over the range of that theta. That will give me the expected value. This is how we do expected value. Probability into that x, probability of x into x. That is my expected value. I hope you remember this. That's what it is. Okay, now let's so for as the examples that I'm talking, we have discussed this already, and I have been mentioning this. Watch the previous recording, in that it will be present, and I'll take the example as it is, and I'll then proceed from here. So example 1. Example 1. So discussed in previous video. Watch that. Without that it is not there. So I'll just give you highlights of that. Okay, so what was the prior there? Prior was f of theta is equal to 1 uniform 0 over, okay, and if I want to write, so it introduces beta function also. So this same thing in this is beta 1 1. Okay, this was uniform. So this is beta 1 1, or I can, in terms of uniform, I can write theta is uniform 0 1. This is uniform in this range 0 to 1. Okay, this is my prior. What was my likelihood? So what, after this we calculate the posterior likelihood, etc. See the calculation there. Okay, calculations prior, posterior. What was the posterior there? F of theta given x, theta given x is equal to this was, okay, so let me write it down so that it's clear for you. So the likelihood was Bernoulli. So this was Bernoulli. The underlying distribution was, assumption was, the distribution of the data was Bernoulli. So we are doing Bernoulli trials. So their likelihood of f of x given theta was equal to theta to the power n1, 1 minus theta to the power n minus 1, where n1 is number of ones. n1 is equal to number of ones in n trials, and n minus n1 will give me number of zeros. So this is, theta was probability of 1 success, and this was probability of failure, and we have to find this parameter theta. And after doing this analysis, we found out that posterior was, what was the posterior value, and we discussed about beta functions also there. So that was theta n1, 1 minus theta n minus n1 by beta of n1 plus 1 and n minus n1 plus 1. Okay, and what is our beta? Just to give you this is integral 0 to 1 t to the power a minus 1 and 1 minus t to the power b minus 1 t of t. So this is our beta function. So this is the beta function or beta distribution that is used to simplify complex integrals, and we used it as it is where our integral was there. As I told you, calculating the integrals are difficult, and we use known distributions, and beta is one of them. This is called beta function or beta distribution. Okay, and if we plug this in, and then after this we got that this is a beta function with n plus 1, n1 plus 1 and n minus n1 plus 1 when theta was uniform. Okay, and now let's calculate. So this is known. So till now we have done in the last video. Now let's calculate. So we know the distribution, everything. So this gives me the distribution of the posterior. So I have got the distribution of the posterior based on the prior. Okay, so what will be the MMSE now? Theta MMSE. So I want to get one value out of that. What will be my minimum mean squared error? For which theta in this distribution will I get the minimum mean squared error? So I have to find the mean around which. So this will be integral. So this is a continuous. I'll do an integral 0 to 1. Okay, and this will be theta into the probability distribution. See, I have multiplied theta here. Theta. So this is a multiplication of theta and probability. So this is your posterior into theta. So I have got the posterior and I have multiplied with theta. So theta I have done multiplication, and let's multiply it with the posterior. What is the posterior? Theta to the power n1 minus 1. No, n1 and 1 minus theta to the power n minus n1, and this integral is also there. Theta is in the range 0 to 1 because it is uniform. This integral will be in the range of 0 to 1, and this is divided by the beta function that we had, n1 plus 1 and n minus n1 plus 1. Okay, so what will be this value? This will be equal to, so this theta will come here, so this will become 0 to 1 theta of n1 plus 1 minus theta n minus n1 remain as it is, and this is a beta function already, n1 plus 1. Okay, and this is n minus n1 plus 1. So this is again a beta function because this is the integral theta and 1 minus theta. This is an integral n minus, and what is the format? A minus 1 is equal to n1 plus 1. So let's find what will be the parameters a and b of theta. So you have to find a is equal to a minus 1. A minus 1 is equal to n1 plus 1. This implies a is equal to n1 plus 2. Similarly, b minus 1 is equal to n minus n1 plus 1. So b is equal to n minus n1 plus 2. Sorry, n minus n plus 1 is not there. 1. This is only 1, right? So I have to make to compare to only this. Here n plus 1 is there, and here n minus n1 is there. So n minus n1, this one will come here, and then this 1 plus 1 came here, 2. So what will be my beta distribution corresponding to this? A is n1 plus 2 and b is n minus n1 plus 2. So my theta predicted, so I'll put a hat, this is prediction symbol, is equal to, in the numerator is a beta function of n1 plus 2 comma, this is a, and b is n minus n1 plus 1, and the denominator is beta of n1 plus 1 n minus n1 plus 1. This is for uniform prior. Okay, I hope this is clear. This is simple. So we just calculated the mean or the expected value, and the expected value was is the posterior into theta into because the expected value of something is probability of x into x, and this is summation or integral, whatever, depending upon the case, and this will give me the summation of the whole range will give me the expected value, and that's what we did with the posterior. After when we have got the posterior, we have got the distribution. That means that is giving me the probability distribution, multiply it with the each value of the theta, and then get the value out, and we got that this is this value. Okay, and let's do similarly for the example 2 also. Similarly for the example 2 from previous video. where the theta was biased towards 1, previous video. Here I'll take the same example. So my f of theta is equal to 2 theta. 0 is less than x, 1, 0 otherwise. This is my prior. Okay. So this was my prior earlier. So similarly, if you calculate this, so this is my prior, same thing, and now you are seeing that this is 2 theta. So I'll just calculate the posterior quickly. So my posterior will be, what was the posterior for that case? I'll just refer from the last class. F of theta given x is equal to, this was theta to the power n1 plus 1 and 1 minus theta to the power n minus n1, and the denominator was a beta function of n1 plus 2 comma n minus n1 plus 1. Okay, so this was my posterior. So posterior is already there. Okay, right. So after this, if I have to calculate my theta MMSE, theta predicted MMSE. Similarly, it will be expected value of theta into the posterior. Posterior is here, and the integral will be 0 to 1. And after you do the calculations yourself, this will be similar calculation as it is, and what we will get finally is, this will be a beta function of n1 plus 2 is here. Okay, and this will increase by further one more, since it will become, if I multiply by theta here, right, let me do it quickly for you. Integral 0 to 1, this is 2 theta into theta n1 plus 1 minus theta n minus n1 plus 1 by, this is beta of n1 plus 2 comma n minus n1 plus 1. Okay, and this 2, and here also that 2 will come. Okay, this will cancel out, and this theta will increase 1, because this theta will multiply here also, both of the places. So this will become, and this will become finally, just do the maths, this will become a beta function of n1 plus 3 n minus n1 plus 1 by beta function of n1 plus 2 n minus n1 plus 1. So this is your theta MMSE, that is minimum mean squared error for that estimate. This is your estimate. Okay, this is your estimate. I hope this is clear. So this is for the biased, this is theta is more biased towards, you remember this was this y is equal to 2x or theta is equal to 2 theta. So as you go towards 1, this is more biased towards 1. That was the distribution of that theta, and this was uniform. This is your minimum mean squared error estimate for, this is different from the uniform case. This is for uniform prior, and this is for biased prior, biased towards 1. We saw both the cases. One in the first one, in theta map we saw bias towards 0, and in MMSE we saw bias towards 1, so that it gives you idea. It can be, prior can be biased towards any of the values. Okay, and depending upon that we will get the final outcome.